Have you ever wondered how well we can predict when someone is looking for a job change? That is a tough question to answer and a question a lot of people would probably like to know. So today we are going to go through my process of trying to answer this question using data. To start off, I'm going to talk a little bit about the data. I found this public data set through Kaggle, and the data is from an anonymous company. This company hires many data scientists, and they provide a training course that many people sign up to take. However, not all of them are actually looking for new employment and take this course instead to improve their skills. The data set they provide has about 19,000 observations with 14 demographic variables about each candidate that takes their course. Here are the variables that the dataset provides. It includes employee ID, a city code, city development index, gender, if they had relevant work experience, whether or not they were currently enrolled in university, education level, what their major was in college, how many years of experience they had, current company size, current company type, years at current job, hours of training completed, and the target variable, which is whether or not they're looking for a job change. Now that there's been an introduction to the data set and an introduction to my research question I'm trying to answer, here is how the rest of my presentation will go. I will talk about pre-processing, hyperparameter search, training a final model, and the results from all of this. Data pre-processing. At first, I performed exploratory data analysis. Things that stuck out to me were many missing values as well as slight data imbalance. On the right side, we can see that the slight data imbalance of the target variable, where only 30% of the candidates actually want to change their job. In order to deal with missing data, we use simple imputing. For continuous variables, we used a median imputation, and for discrete variables, we imputed a new category that I called unknown. After we had to encode our variables, uh, where we used one-hot encoding for our nominal discrete variables and ordinal encoding for our ordinal variables. By using ordinal encoding on some of our variables, it gives us faster runtimes. Since the data was imbalanced, I tried to use sampling techniques such as undersampling, oversampling, and SMOT. However, these techniques did not yield better results on the training data. I also dropped the enrollee and city ID variables before going on to modeling since they were unimportant features. Algorithms. I tested two different algorithms to search. I looked at two tree-based methods, extra trees classifier and random forest classifier. There are many similarities between the two techniques since they both are tree-based methods. They both use a random subset of features when training their tree, and they also use the same hyperparameters that we can search through. Some difference between the two algorithms are that random forest uses a bootstrap of the sample, meaning that each time a new tree is estimated, a percentage of the data is left out, while extra trees uses the whole data set. Also, when training their single tree, random forest tries to find the best place to split the data, while extra trees uses a random split. Now that I've talked about some of the similarities and differences, let's look at how I found the hyperparameters. For hyperparameter tuning, we used random search, trying to maximize on F-score using a beta of 0.5. The reason I chose a beta of 0.5 was trying to maximize precision since we want to be able to correctly predict that someone is looking for a new job while also accounting for recall and keeping the maximum pool of possible candidates big. We also used a 5 crossfold validation while trying 100 different combinations of hyperparameters. The hyperparameters I tuned were the number of estimators, max depth, loss criterion, min sample split, min samples per leaf, max features, and class weight. Here's a visualization of the final pipeline I came up with. In the end, the random forest performed better than the extra trees. The non-default parameters that produced the best F-score were a balanced class weight, tree max depth of 200, minimum samples leaves of 3, minimum sample split of 5, and using 200 trees for the estimate. Here we'll talk about the final test metrics. When creating the train and test set, I used 80% of the data provided to train the model and 20% of the data to test. I also did a stratified split so that there was an equal amount of targets in the train and the test. I got a test accuracy of 79.79, meaning that out of the 3,800 predictions, we got 79% of them correct. We also got a precision of 0.56, meaning that when we predicted that someone wanted to change their job, we got it right 56% of the time, which is better than completely randomly guessing. Our recall score was 0.74, meaning that we were able to see 74% of all candidates that actually wanted to change their job. To conclude, let's summarize our findings. We made a final random forest model that performed okay on our test set. The business use for this model is that with better prediction power, we can use the model to save money in terms of the hiring process. If we're reaching out to less candidates who aren't interested in the job, we can save both our resources and our time. Some limitations to this model is that it can probably only use specifically for this company since the data is all within the company, all within this one company. There may be some similarities or patterns with other companies, but it's hard to extrapolate data from that. Some next steps to improve this model could include getting more data as well as sacrificing more recall for better precision since there's such a large candidate pool. Thank you for listening to my presentation. If you want more information or to look at my code, there will be links in the description that can explain more.